Welcome everyone. I am Emanuele Mendicelli, a PhD student in physics at York University in Toronto. Today I will talk you all about our last published work that used the D-Wave quantum annealer. Before starting, I would like to stress that this is a non-technical talk. I did my best to reduce at minimum the technical jargon. So in this way, I hope you can better appreciate in which way we use the D-Wave quantum hardware. Okay, this work was done inside this research group that is made by Sarmeda Raman, that is a graduate student at York University, Professor Randy Lewis, and Sarah Powell, that is an undergraduate student at York University. To let you all better appreciate our research field, I think it's better to just give a very short idea of our research field. And in this way, then you can appreciate why we ended up to use the quantum computer. Okay, our research field is inside particle physics. Particle physics is a branch of human knowledge that its main goal is study the smallest object that are present in nature. So in doing that, there are used very precise experiment, very complex, in very big labs like the CERN lab in Geneva or the Fermi lab in the United States. Together with the experiment, there are people creating theoretical models, and the goal is discover new fundamental particles and characterize their properties. Saying this way, it seems that particle physics is very distant from our everyday life. There is no implication. But this is not true because there are so many applications. One sometimes wrongly one thing that the nuclear bomb. In reality, the nuclear bomb is an uncontrolled event. But what is in reality comes directly is a direct application of our experiments are in the field of medicine, in the fights against cancer. One example is the radiation therapy, using radiation to bomb and burn cancer. And then something that it's start to be in our present and it will be more used in the future is the hadron therapy. Instead of using radiation to bombing the cancer, we use proton. Okay, so within particle physics, because we are theoretician, we do research in the field of lattice gauge theory. This is a theoretical framework in which theoretical models are directly formulated to be studied through simulation supercomputers. Basically, in these models, the particles can only move in a discrete space, in a limited discrete space. In this way, with this model, we can predict particles and then advise the experimentalists to find them, and then we can predict their properties. So this is a theoretical framework that it was introduced in the late 70s, but even if there are so many goals achieved by this approach, there is a main roadblock that is still present since the origin. Basically, we cannot study any dynamical process in real time. If any, like even the collision of two particles or a propagation of a particle, this cannot be observed as we want to observe with our eye. This is because when we try to do the simulation, there is a part of the calculation which is not possible to calculate effectively with a classical computer. Basically, because there is an integral that is highly oscillating, and this it's at the moment impossible to solve it in a finite time. So the motivation, the why we are here using quantum computer is because from the conceptual point of view, we know that many questions in particle physics affected by the so-called sign problem can be solved effectively using a quantum computer. If it's not in this present time, it will be in this recent future. Okay, now that we have more or less an idea in which field we do research, we present our model. This is our model. In a most simplified way, this model describes massless particles, and these particles, they can move only in a ring-shaped lattice. Now, if for the sake of the talk, we simplified our model, we just consider two plaquettes, the smallest possible lattice, the model is just represented by this 4x4 matrix. All the information that we want, the energy of the particle, their mass, the way that they propagate, all of this information can be extracted simply working on this matrix. The easiest things to do is diagonalize the matrix and find the eigenvalue and the eigenvector. And this, they tell us the energy of the states and what kind of state it is. For a small lattice, this study can be done on a classical computer, but we decide to try to do that on a quantum computer. Okay, in doing that, because we want a solution as a real number and the states characterized as a real number, we needed to use this algorithm called the quantum annealer eigensolver. This is a quantum algorithm developed by this group of researchers and chemists from Los Alamos University and Marquette University. Basically, they introduce an extra Lagrange multiplier lambda in the QUBO equation. This parameter has to be tuned by the user to get the correct solution. The other thing that there is in this algorithm is that to represent the number, to represent a real number, k qubits are used to represent them. So when one does a run using this algorithm, at the end, when you get the results, one doesn't want to have just the value of the qubits, but one want to have a solution as a real number. So if we use 1 qubit to represent the numbers, the solution that we have can be only -1 or 0. If we increase the number of qubits used to represent the real number it can have now 4 options. So more qubits we use to represent the real number, more this real number can be identified precisely. So to keep in mind, k, it determines the precision of our calculation. Okay, now let's see the steps that we use when we try to use to our best the QEA algorithm. The first step is to find the optimum lambda and the number of qubits needed to achieve a result that is in agreement with the correct one. So normally this step is done on a simulator so that the computational cost is very low on the actual quantum hardware. So from this panel, we can see this first point, this first step. Here we have the energy of the system of the lowest states versus lambda. Immediately here we can see that using 2 or 3 qubits to represent real number are not enough. Like we can see that the green and the yellow line are so far away from the exact results, that is this red dashed line here. So to achieve a result in agreement with the correct one, we need at least 6 qubits. And we can see here that with 6 or 8 qubits, it exists a range of lambda in which we have a result that is in agreement with the correct one. So once we know k and lambda, we can go on the actual hardware. And when we go to the actual hardware fixing k and lambda, we have to tune just the chain strength. We do the simulation and we repeat these steps as many times, increasing the number of qubits just to see if the results improve. Normally, when we send the algorithm to the actual hardware, we have to increase the number of qubits needed to represent a real number. Okay, these two steps are summarized here in this panel. We have again the lowest energy of the system versus the number of qubits used to represent a real number. And in this, we have the data for different choice of the optimum lambda and the chain strength. And we can see here that the best combination is the blue one at this point here, when we use 8 qubits to represent a real number. So these steps that I have presented in this panel, they were always done in a controlled way, in the sense that there was always the classical solution. But this can be done in a blind way. One can do the simulation and then quote as a correct result, so as a final results, the one that has the lowest energy. Because this we have to keep in mind, it's a well-known thing, it's like a physical system, the energy of a physical system, of a stable physical system, is always the smallest one. Okay, so when we try to use this algorithm with these steps to extract some physics, we realized that we were not able to achieve the precision that we wanted. So we extended this algorithm and we created what we call the adaptive QEA algorithm. Basically, this algorithm that we proposed, this extension of the original algorithm, runs several times the QA algorithm, and in each step it uses as a starting point, as a starting state, the one that it was obtained in the previous round. So in this way, each time that we do a steps, the solution is more finely determined. To have a better view of what is going on, is like, we know that a quantum nonlinear is a device that is able to find the minimum of a surface. With our algorithm, in each step, we are zooming this surface around the minimum. So we do a step, we zoom, and then we re-ask the quantum nonlinear to find the minimum around the area in which before he found a minimum. So in this way, he can find a deeper minimum, or he can find that the previous minimum was deeper. In general, with this algorithm, we have a faster convergence using fewer qubits. And this is very important, because less qubits we use, less is the chance that we have a chain break. Okay, so here is a study of the convergence. Like here we see all the proposed algorithm fastly converge toward the exact results. Here the black points are 3 different runs from the actual quantum hardware. And we see how it fastly converge toward the exact results, that is this black dashed line. Now let's have a look to our algorithm in action, just to extract a little bit of physics. And here in this panel we have the ground state energy versus the gauge coupling X. And these points, they come from the actual hardware for different value of qubits used to represent the real numbers. Now, in this animation, we will see what will happen when we increase the number of qubits. Number of qubits and the steps of our algorithm. As we can see, increasing zeta, the number of steps of our algorithm, there is a global convergence toward the exact results, that is this solid line. And the other thing that we can notice is, like, using k plus zeta equal to 8 is already enough, because going on with the steps, there is no an important improvement. This means that we reach the limit of precision. Okay, so now this algorithm can be used to extract more physics from the model. And the first thing that we can see from these two panels is, like, the agreement between the exact results, that is the solid lines, and the data set, the points coming from the hardware, it's quite good. It's quite good. And the interesting things from the left panel is that if our model is represented by a matrix like 3 by 3, 5 by 5, we can use the QEA algorithm with a number of qubits equal to 7. But if our model is represented by a matrix that is 14 by 14, in this case, we need to use our algorithm. Okay, this is an interesting slide because it looks in the future, and it has certain conceptual points that are very important. This is time evolution. These two panels tells how the system evolves in time. As I said before, this is very hard to do on a classical computer if the lattice is very big. So normally to extract physics that then it's found in experiment, one needs very big lattice. And for very big lattice, this kind of calculation cannot be done on a classical computer because it scales exponentially, meaning that the execution time, it became exponential with the size. So, but for small lattice, for small space, this can be done on a classical computer, and this is the solid line. And again, the agreement from the quantum hardware and the classical, it's quite impressive. But the other important thing is that in the future, when the quantum computer will be less noisier, this will be a task mainly done by quantum computer because classical computer cannot do that on large. The other important things, the conceptual point is that to do this, to let the quantum annealer by D-Wave doing time evolution, we needed to use this different technique, the Feynman clock. This why is important because the challenge of the future is find new way of simulating the theory using the new hardware that are the quantum hardware. And this is things that we have to look for the future. Okay, we are arrived to the conclusion. There are a few things that we want to stress. We want to say that in the present time, in the so-called noisy intermediate scale quantum era, that means it's an era in which there are quantum computers but are still noisy, simplified particle physics model can be studied on the D-Wave quantum annealer in a very satisfactory way. The algorithm that we introduce uses fewer qubits and it's able to solve larger Hamiltonian. Our algorithm it was further studied by this group of researchers. One of the last thing that we want to stress is that our main goal was mastering the use of the D-Wave annealer through the introduction of a new way of simulating the theory. And this is a key point important for the future. Find new way of using the quantum hardware. We like to stress which are, for us, the feature of using D-Wave, compare them with the gate-based quantum computer. First of all, the mathematical model can be directly submitted to the hardware. One takes the Hamiltonian of the matrix and directly sent to the hardware. This is in contrast with what happens on a gate-based quantum computer, in which normally one has to rewrite the model using gates. The other point is that this is a technical point, but it's very important in particle physics. When we use an annealer, we can use only the physical space of the system, only the physical Hilbert space. Basically, we don't need to introduce artifacts for the sake of doing the simulation on the hardware. And this is important because normally in a gate-based quantum computer, one needs to introduce artifacts. Another point is like we were able to achieve, and now people can achieve precise results on the quantum annealer without using any kind of error mitigation technique that sometimes are costly and challenging from the computational point of view. What we noticed that for the same model, the quantum annealer normally requires more qubits than the one compared to the gate-based quantum computer. And maybe this will change while the algorithm will change and the hardware will change. With this is all, and I thank you all for your time and your attention. Goodbye.